Good afternoon, everyone, and thank you for joining Beyond Chemistry, choosing the right HPLC column for the real world. I'm Alex Nase with MacMod Analytical, and today we are joined by Dr. Lee Polite, founder and president of Axion Analytical Labs in Chicago. Before we start, I have a few housekeeping items. We will send a link to a recording of the webinar and a copy of the slides via email after or sometime next week. And please post any questions you have in the Q&A window at any time during the presentation. At the end, we will gather them and address as many as possible during the live Q&A. It is now my pleasure to introduce Dr. Lee Polite. Dr. Polite is the founder and president of Axion Analytical Labs, a premier chromatography training and consulting firm. Since 1995, Axion has trained more than 14,000 professionals in 17 countries and has supported every major pharmaceutical, chemical, and petroleum company in the United States, along with agencies including the FDA, DEA, EPA, and Homeland Security. He earned a PhD in chromatography at Virginia Tech under Dr. Harold McNair and an MBA in strategy and marketing from the Kellogg School of Management at Northwestern University. For more than 30 years, he has taught chromatography worldwide, serves as a lead instructor for the American Chemical Society, and teaches graduate level chromatography at Illinois Institute of Technology. Dr. Polite is known for making complex theory practical and directly useful in the lab. I had the pleasure of accompanying MacMod's sales team who attended Dr. Polite's class and can personally share that it was outstanding and I learned a great deal. We worked through real lab problems from resolving critical pairs to managing pressure limits and scaling methods, and I left with clear decision rules for particle type, particle size, surface area, and carbon load that I use in my work. So I know you are in great hands today. Dr. Polite, thank you for being with us. The floor is yours.
Great. Thank you, Alex. Thank you for the invitation to be here. I always love talking about chromatography if anyone is willing to listen. So, when I was given this topic, the title itself, Choosing HPLC Columns in the Real World, I was thinking, is that like a MTV thing, like the real world? I was trying to find some MTV, and then I figured you guys are probably not old enough to remember that old kind of stuff. So this is, I'm always known as the practical hands-on chromatographer. So I want to take you through how we choose a column, but I don't skimp on the details. I want to make sure we go through all the theory behind it as to why we actually like the columns, why we choose the columns that we're going to choose. So I'm actually here with a live audience. There's a bunch of folks here in the room. We're teaching a hands-on HPLC GC class here in Chicago. We just finished lunch today with surf and turf. The lobster was everyone liked the lobster. The steak, some people complain about the butter sauce, but the rest of okay, I'm just kidding. We really didn't have surf and turf for lunch, but we just finished lunch, and we're sort of knee deep in the HPLC part of the class. So this is perfect timing to talk about choosing an HPLC column. So really, to me, a couple of ways to look at this. I guess I would start by saying that LC is the world's most popular analytical tool. It's the world's most powerful analytical tool. It is used to figure out what's in stuff. So if we think about LC, the way HPLC works is it separates complex mixtures into pure compounds. So you're given a mixture. Maybe it's a blood sample, maybe it's a urine sample, maybe it's a soft drink sample, and that's a mixture of chemicals. And our goal is to figure out what's in it. So in chromatography, the way we're going to figure out what's in something is by separating it. So chromatography, HPLC, should separate complex mixtures into pure compounds. Now, we may ask the question, why do we separate? Well, we separate to identify. We separate to quantify. We separate to purify. But step one is to separate. So for example, if you have a cup of coffee, you want to know is there caffeine in the coffee, we would look for the caffeine peak. We would separate caffeine from all the chemicals in coffee and look for the caffeine peak. If you wanted to measure caffeine in coffee, we would not only separate the caffeine peak, then we would measure the size of it. If you wanted to purify caffeine from coffee, we would collect that peak once we separated it. But you get the idea that step one is to always separate. Now, separation is not that complicated, but everyone expects it to be. In fact, most people sort of say, we cannot understand the separation, it is what it is, but that's not true. We can understand it. In fact, we are in charge of it. So what I'd like to do is to sort of take you through how chromatography works, the underlying technology, and with that knowledge, we could then look at a series of columns and easily choose the right column for us. So I just want to adjust this to make sure you guys can see my whole screen here. I do apologize. I think this guy is sort of in the way, maybe. Okay, so when you're looking at chromatography, the separation, we think of all the parameters in LC. We got column length, diameter, we have particle size, we have mobile phase, we have temperature. It turns out that there's only 3 things that can affect your separation. I'm going to tell you what they are, and I'm going to show you, more importantly, how you're in charge of them. But before we get there, let's talk a little bit about what chromatography is and how it works. So to do that, we're going to talk about Kool-Aid. And you're thinking, Kool-Aid? How do we talk about Kool-Aid and chromatography? But this is one of my favorite examples of chromatography. And what we're going to do is, I've got a packet of Kool-Aid here. And Kool-Aid is one of my favorite things. Remember when I was a kid, we used to drink the stuff, we put a boatload of sugar in it, it tastes great. But it turns out that this is artificially flavored and artificially colored. I hope I didn't burst anyone's bubble out there. If you thought this was real grape juice in a packet, got bad news for you. There's nothing natural in this packet. It's just chemicals that are mixed together to look like grape juice and taste like grape juice. So if we have colored chemicals in this packet, we should be able to separate them by chromatography. So we're going to do a real HPLC separation for you right here in front of your eyes. And to do it, we're going to use a little what's called a solid phase extraction cartridge, SPE. So I do have pictures of this to go along with it. So in case you're not being able to see this very, very nicely. So this little cartridge is used for sample prep. It's great for sample prep, but it's a fully functional HPLC column. This is packed with a C18 particle. The most popular stationary phase in all of LC is C18. So we're going to run a sample through the C18. Now, this is not an analytical column. The analytical columns we're going to learn later on have really small particles, 5 micron, 3 micron, 1.8 micron. This thing has 40 micron particles. So they're gigantic particles, not high resolution, but enough resolution to do separation of the great Kool-Aid components. So a little bit about the science behind this. We're going to talk about polarity. Polarity is a really important point in chromatography because we use that to describe GC columns, LC columns, mobile phases, how things separate. We got to understand polarity. But as I was joking with these guys earlier, that professors take 2 years to explain polarity. I apologize for the professors out there, but you know who you are. You take 2 years to explain polarity because you got to go through electron orbital theory and electron density, electronegativity, blah, blah. So I'm going to give you my 2-minute version of polarity. You ready for this? Water is polar. Anything dissolved in water must be polar by definition. Like dissolves like. So if something dissolves in water, it is polar. If something does not dissolve in water, it is nonpolar. So that's all you need to know about polarity. That's the whole world of polarity. Let me prove to you that you understand it. If I were to give you a packet of sugar, I got a packet of sugar, and I ask, is it polar or nonpolar? And your answer is going to be polar. Oh, how do you know? Oh, it dissolves in water. So then I've got a salt shaker, some salt in it. Is it polar or nonpolar? It's polar. How do you know? It dissolves in water. Excellent. What about olive oil? I like it for salad dressing. Is olive oil polar or nonpolar? It's nonpolar. How do you know? It doesn't dissolve in water. So that's the whole world of polarity. That's all you really need to know. And we use that in HPLC because in this case, my little solid phase extraction cartridge is packed with C18. C18 is very nonpolar. As mobile phase, I'm using water, which is very polar. So when we do a separation, the analytes have a choice. They can stick to the polar mobile phase or the nonpolar stationary phase, and they're going to distribute themselves based on their polarity. So I'm now ready to introduce my sample. I have a Kool-Aid sample that was freshly made up. And what I want to do is I'll start passing the Kool-Aid through this cartridge. And hopefully what you're seeing is you're seeing the liquid drip through. And hold on a second, just in case you're not seeing it. This is the still version of what it would look like, but I'm doing it live for you. So as you can see, as I'm pushing the Kool-Aid on the column, the colored chemicals are sticking to the column. So we have no color coming out and all the color is on the column. So at this point, if we ask, what do we know about these colored chemicals? Are they relatively polar or nonpolar? Well, they're relatively nonpolar. How do I know that? Because they're stuck to a nonpolar surface. There's no surprise. They're telling me I'm nonpolar by the choice they've made. So I could keep going, pushing water through here, but these guys are not really going to move. They like the stationary phase. They really don't like water. So if I want to elute them, so in chromatography, it involves getting peaks on the column, then off the column. I need something stronger than water. So on a polarity scale, if water is here, C18 is here. I need something in between, and that would be ethanol. So ethanol, methanol, acetonitrile are right about here. So I have a solution. It's a 10% ethanol solution. I'm going to hook this up to the cartridge, and I'm going to start pushing this through. And as this moves through the cartridge, hopefully you're starting to notice that there's a separation occurring. So there's not one color in grape Kool-Aid, there's two artificial colors, and those two colors are red and blue. You're right. You remember kindergarten? What did you learn in kindergarten? Red and blue make purple. So I have two chemicals in here, a red one and a blue one. Which one is more nonpolar? Which one is more hydrophobic, the red or the blue? It's the blue. How do you know? It's stuck stronger to the cartridge. The cartridge is nonpolar. This says I'm really nonpolar. This guy says I'm sort of nonpolar. So with a little bit of luck, I can change collection cups here, and I can collect pure red in one bucket. That's pure red chemical. Unfortunately, the blue, it's not moving very fast. This would have to be a 5-hour webinar for me to get the blue off the column. So what we need is a different mobile phase. Now, you're thinking, do I need a stronger mobile phase or a weaker mobile phase? Stronger, good, good. Do I need more ethanol or less ethanol? More ethanol. So here we have a 75.5% ethanol. And with this, as I start to push this through, hopefully you'll see in just a moment, you'll see that the blue will start to move. So what I just did for you here was what we call a gradient HPLC. I started with a very weak mobile phase. A mobile phase, 100% water. It was so weak, the analytes sort of said, you know, we don't prefer that water. We really prefer the C18. And then I upped the game to 10% ethanol. And with 10%, I was able to elute the red. And then I upped it to 75% ethanol, and I'm able to elute the blue. So that is what we do in HPLC all the time. It's called a gradient, where we start with a weak mobile phase, and we program up to a strong mobile phase. So with a little bit of luck, I can separate the three fractions of grape Kool-Aid. And those three fractions would be polar, the semi-polar, and the non-polar. I know what you're thinking. There's nothing in the polar one. Well, just because you can't see it doesn't mean there's nothing there. You should never taste anything in a laboratory, but at some point, you know, I had to taste this. It's really sour. This is all the acids, the ascorbic acid, the citric acid that they put into Kool-Aid to make it tart. And what's interesting here is, unfortunately, you can't participate in this part. Not that I'm going to drink it, but I'm going to smell it. And it turns out that the grape flavor ends up in the blue color. I wish this were smell-o-vision. I could stick it up there, and you could agree with me. But the people in this room can attest to the fact that this really smells like grape flavor. They're nodding their heads. Yes, trust me on that. Yes, yes, they're saying yes. Good. So what's cool is the blue color is not grape flavor. It's coincidence. I don't know what they use for artificial grape flavor, but I know this. It's pretty nonpolar. How do I know that? It came off the nonpolar fraction. So that simple little experiment, which I think is a great way to demonstrate chromatography, is also a great way to prepare samples, to look at different fractions of your sample and find out which one smells bad. Is the polar, the semi-polar, the non-polar? So in real life, I've used this a bunch of times for real problem solving, but I love using it as a demonstration because that is real HPLC. This is the same technology. I've got 10 LCs in my lab over there. This is the $5 version, and that's the $50,000 version. Same chemistry, but instead of me using my thumb to push over the column, since we have smaller particles, my thumb's not strong enough, I need a high pressure pump. And now that we have a nice steady flow, instead of using our eyeballs as a detector, we're going to use a UV detector. So it's this, we're just going to mechanize it. So hopefully that helps to sort of solidify the concept of LC. And I'll just flip through the rest of the slides. There's the cartridge with the colors on it. Here I'm with the 10% ethanol eluting the red. And then I am eluting the blue with the 75.5%. So now we have the three different fractions. And here's me drinking the Kool-Aid. Like, don't do that at home. Don't do that at home. Okay, so that's my Kool-Aid chromatography. And that to me should open your mind up a little bit and be like, okay, that was sort of cool, but how did that work? What was it? What was the underlying technology? You know, I need to separate red and blue. And in real life, you've got your own chemicals you're trying to separate. And if we ask the question, how do we separate things? And most people will say, well, we can't understand that. That's physics, it's chemistry. We can't understand that. Yes, we can. And let me explain it to you. So it turns out that there's only three things that affect your resolution. I know there's 300 things on the LC to set, but there's only three of them that affect resolution. What are they? They are capacity factor, selectivity, and efficiency, just as I'm showing you on the slide. So K is capacity factor, alpha is selectivity, N is efficiency. And our goal in life is to separate our peaks. Mathematically, that means we need a resolution of 1.5. So I have a little picture of two peaks. 1.5 resolution means I've just barely touched the baseline. If you have resolution greater than 1.5, that's fantastic. Resolution less than 1.5, not acceptable. So we have our first quality check of our chromatography. And we can answer the question, do I trust my results? Have I produced valid data? And the first question is, do you have good resolution? Is your resolution greater than 1.5? If so, then I trust your data. If not, I don't trust your data. You got to go back and fix it. So we have a pretty clear mathematical line where we know we can trust the data or not, and that is the 1.5. So now the question is, how do we get to 1.5? So the first term, capacity factor, we like this to be between 1 and 5. The important part, we like it greater than 1. So I'll give you the equation for all those math geeks out there, but for the rest of us, we're like, okay, Lee, we're with you. You've convinced me the capacity factor is super important, but my LC doesn't have a button that says capacity factor. How do I make it bigger? That's really simple. All you have to do is weaken the mobile phase, make the mobile phase weaker. What does that mean? Most of us are doing reverse phase. We're using methanol water, acetonitrile water. Water is weak. Add 10% more water, absolute 10% more water, and you will double or triple your capacity factor. So capacity factor, arguably the most important parameter in separation, the most important thing that we need to resolve peaks, and to adjust it is free. It costs you nothing to add more water to the mobile phase. In fact, you argue it's a little cheaper because it's cheaper than acetonitrile, and that has the biggest impact on your separation. So the first thing we look at, if I'm doing method development, method optimization, method troubleshooting, I'm going to look at the capacity factor and ask the question, is it greater than 1? If it's not greater than, if it's less than 1, then I need to fix the mobile phase. Don't do anything until you fix that mobile phase strength. So capacity factor tells you, did you choose the right percentage of methanol or percentage of acetonitrile? So think about this. You're going to develop a method. You're going to have a certain percentage of acetonitrile or methanol in there. How do you know what the right answer is? Should it be 10%, 18%, 42%, 91%? Well, the right answer is the percentage that gives you a capacity factor of at least 1. Let's make this even simpler. You've got 200 compounds in the sample. There's only one compound. There's only one capacity factor that matters, and that's the first peak. So I don't care how complex your sample is, the mobile phase strength is set to make the first peak happy. So capacity factor, most important parameter, it's solvent strength. It answers the question, do I have the right percentage of methanol, percentage of acetonitrile? Now, if you're doing ion exchange, the same thing. It's asking your ionic strength, how much salt do you have in there. If you're doing normal phase, it's the same thing. You know, hexane is weak, and whatever you're adding to it is strong. So if you're using gas chromatography, how do we get a higher capacity factor? How do we do that? We lower the temperature of the column. So there's always a way to make capacity factor bigger. It's always free, and that's the first thing we look at. So that is solvent strength. That's going to ensure that our analytes can spend time interacting with the stationary phase. Okay, so next up is selectivity. Selectivity is a rule, 1.2. It's easy to calculate. It's a ratio of capacity factors, but it's harder to understand. So I'll start off by saying, in the GC world, this is real simple. It's a function of your stationary phase in GC and nothing else. In LC, it's a function of a lot more than just that. It is primarily the stationary phase, which comes from the column, but it's also the mobile phase. Not the mobile phase strength, that's the K term. This is the mobile phase chemistry. Methanol is different than acetonitrile, is different than THF. These are different selectivities, and that's important to know because the only time we care about selectivity is when we don't have it. When you got nothing, your peaks don't separate, you're wondering, oh my gosh, how do I change this mysterious term? We change it by changing the chemistry. So either we're going to change the stationary phase chemistry or we're going to change the mobile phase chemistry. In my mind, the easiest thing to do is the mobile phase. So I go from methanol water to acetonitrile water or THF water. Those are huge changes in selectivity, and oftentimes that's going to solve your problem. If that doesn't work, then we're going to start looking at stationary phases. We're going to look at C18s and cyanos, aminos, and amide columns and hydroxyl columns. So we're going to look at different stationary phase chemistries as well. So I highlighted the column stationary phase because this is, to me, sort of a column talk, and I'm going to get into a little detail on that in a bit. And then the last term we have is efficiency. This is a measure of the skinniness of the peak. The bigger the number, the better. So if I want more efficiency, if I want to go out and buy a new column, first of all, there's the equation for it. If I buy a new column, I can buy a longer column, guaranteed to give you more efficiency. I could buy a column with smaller particles. That's huge. It's our biggest parameter in LC. We could do that. We could optimize the flow rate. We could minimize the extra column volume. But these are all ways to make the peak skinnier, which is going to improve the separation. Remember, our goal here is to get that resolution of 1.5. And here's ways that we're going to get there. So the best approach is you look at your current parameters. What is your capacity factor, selectivity, efficiency? And you figure out which one is bad, which one is the lowest hanging fruit to improve, and then that's the one we work on. Capacity factor is always the easiest. It's solvent strength. Efficiency is easy, longer columns, smaller particles. Selectivity, I would say, is a more difficult one because it's harder to predict if it's going to work. We can predict it's going to change. We just don't know if it's going to change for the better or for the worse. But we'll get more into that in just a bit. So let's take these three terms. Let's talk about the capacity factor. This is your solvent strength. So how do you find the right solvent strength? Later this week, tomorrow, I'm going to be really cruel. Tomorrow, I'm going to hand these guys an unknown. Yesterday, I gave them an unknown for GC, and they did really well. So I'm pulling out the big guns. I can give them a more difficult unknown tomorrow. And their job is to find the right mobile phase strength to separate the unknowns. Well, how do we know when we have the right strength? Well, it's the strength that gives the first peak a capacity factor of 1. So it's all about, let's try every strength in the universe and find out which strength is the right one. Now, when I say that, I mean, in one injection, in 15 minutes, we're going to try every single strength in the universe. Because solvent strength in LC is well defined. We can go from 0 to 100%. We can't go to 1,000%. We can't go to -%. So it's well defined. We're just going to scan through that and see where the peaks elute. So in this case, we call this a gradient. Start with a weak mobile phase, end it with a strong mobile phase. These are the rules for gradient. So initial condition is weak enough to give the first peak capacity factor 1. That should make sense. The first peak is 1. All the rest are greater than 1. So the initial condition when you're setting up HPLC gradient is all about the first peak. Ignore the rest, just the first peak. The final composition is the final peak, right? You got to get high enough percentage to get the last peak off the column. So your sample dictates initial and final. The only thing that you have to decide is how much time you're willing to wait to get from initial to final. That's the steepness of the gradient or the gradient time. So here's the deal. The steeper the gradient, the faster the analysis, but the lower the resolution. That means the flatter the gradient, the better the resolution, but it takes longer. So all you have to do is decide how long do you want to wait and how much resolution do you want, and it's a sliding scale. Let me show you that graphically. These are the same sample run with 4 different gradients. We're going, in this case, from 10 to 100%, I think from 10 to 100, 10 to 100%, and we're doing it in 5 minutes. 5 minutes is a steep gradient. That steep gradient is going to squish all the peaks together. If we go to a 10-minute gradient, we're pulling them apart. We do the 20-minute, we do the 40-minute, we're seeing that we're stretching out the chromatogram. We're improving resolution simply by increasing the gradient time or making the gradient slope more shallow. So that, to me, is the key in gradients. Gradients are all about the slope of that gradient line. In GC, this is temperature programming. In LC, we call this gradients. It's the same thing, and we look at the time it takes to get from initial to final, or the slope it takes from initial to final. That's going to be an indication of the resolution. I sort of describe gradients as writing a chromatogram on a rubber band and stretching the rubber band as much as you want and squeeze it as much as you want. It really is. You really have the ability to pull things apart and squeeze them together just by going to the gradient. So this is a pretty powerful tool that we have at our disposal. Okay, so we got selectivity. Remember the hard one. How do we do that? Well, selectivity is, I take a big cop out here. I say, you know what? I've been doing this stuff for 40 years. And in my experience, pretty much everyone runs reverse phase. Everyone. But statistically, 85% of you are doing reverse phase. That means if I'm doing method development and I have no idea what the sample is, I'm going to assume reverse phase until I see a reason why that's not going to work. So I always say, choose reverse phase. It's probably going to be the one that you can choose. And if not, we'll know when it's not. So I like this little cartoon. And why do we choose reverse phase? I don't know. It just seems to work for most applications. Well, I like this is, then a miracle occurs. Well, the miracle, that's the reverse phase part. But it turns out we do know how it works. We do understand it. And let me give you a little bit more of this. Reverse phase mechanism is called hydrophobic interaction. So it means I have a stationary phase that's very hydrophobic, very nonpolar. It will attract molecules that are very nonpolar, like dissolves light. So the carbon in your molecule is nonpolar. The more carbon you have, the more time it's going to spend in the C18. So it's all about how nonpolar the column is. The more nonpolar it is, the more it interacts with the column, the longer it takes to come off. So this is a separation based on polarity. And the way I look at it is, if our goal is to separate 2 peaks, whatever your 2 peaks are, you're separating these 2 peaks. These 2 peaks have to be different from one another. And we may ask the question, How are they different? If they have different polarities, we're guaranteed to separate them by reverse phase. So I've got two identical molecules, but this molecule has one extra methyl group. Well, that's a huge change in hydrophobicity. That's going to come off a lot later. This molecule has hydroxyl, this one doesn't. It's a huge difference. This one's got an amino, this doesn't. Gigantic difference. This has a double bond, this doesn't. Not a gigantic difference, but enough of a difference that we could usually separate. So you get the idea that any change I make to this molecule is going to change its polarity, which is going to change the retention in reverse phase. So I look at reverse phase as the most generic approach. I don't care what your molecules are. I don't care what kind of molecules they are. If they are different from one another in any way, reverse phase is probably going to notice that difference. So that's why it dominates. That's why 85% of people find that it works, because it is the most generic or the most sensitive technique to see differences in polarity. So reverse phase dominates. There's a bunch of columns. We're going to get into that in a little bit, but this is going to dominate the world of LC. So we look at the different stationary phases. We think of the C18 as it's the dominant one out there. It's the most nonpolar of the nonpolars. But as I go through, I'm going to show you some more details on how we can really tell columns apart. So I love this slide because it shows different chemistries. And with these, one of my favorite ones, the evosphere, the C12. So we think of columns, C18, C8, C30. Where did the C12 come from? It turns out that if you do like mathematical modeling and you ask the question, I want to put the most carbon on this column as possible. So C18s, more carbon, but C18s are so big that they're sterically limited to putting other C18s in between. So C18s don't bond as densely. C8s, much more densely bonded, but fewer carbons. So C12s, you sort of get that best of both, high bonding density and high carbon. So a C12 is going to look just like a C18. In my opinion, they sort of look that same. So think about the chemistry interaction. If we look at the diphenol's got two benzene rings hanging out there, right? They can interact, pi electrons and dipole interactions and stuff like that. The evosphere amide. Amide is one of my favorite columns out there. First of all, C18 is my favorite column, always going to be. But as we go down that path of modified, I'll call modified C18s, the amide column, it has an amide linkage at the bottom of the C18. That allows the C18 to stand up straight in pure water. So C18 does not like water. It's hydrophobic. It's afraid of water. So if we put 100% water on a regular C18, we get what we call phase collapse. The C18 collapses on itself. We get like a little C-tube nub sticking out, and it just doesn't work. So in order to make a C18 stand up straight, we always need a little bit of methanol acetylnitrile present. Conservative number, 10%, maybe get away with 5%. But if I put an amide linkage down here, I can now put this in 100% water and it'll stay straight all day long. The same thing for the aqua. The aqua is what's called a polar end cap. The amide is a polar embedded, the aqua is a polar end cap, and this is great for polar compounds. Compounds that tend to come off in the void volume of reverse phase. You put it onto an aqua column, you start with 100% water, and you pull out all that stuff. So it's cool that there's other columns out there. We love the C18s because it does that hydrophobicity, but we can add some more chemistry by looking at these various columns. When it comes time to, hey, how do I know what column to use? I'm going to teach you. I can teach you how to develop a method from scratch, but there's a shortcut. And the shortcut is go to a column company website, type in your search word, and you're going to find the answer. So go to the MacMob website. I typed in nitrosamines. Really hot topic today, guys. Nitrosamines are the big thing out there. So I'm like, gosh, I want to do nitrosamines. I have no idea how to do it. I type in the keyword, and I got 10 methods out of it. These are the first 3, but there's 10 in there. So let's open up the top method, and what does it tell us? Hey, look at that. It shows us a chromatogram. It shows us the column, length, diameter, particle size, the mobile phase, the gradient conditions, the temperature. It's all been done, and it's out there for free. So before you reinvent the wheel, go to the website, type in the keyword search, type in benzoic acid. You'll get 20 hits of benzoic acid and all the different conditions that you need. So methods exist out there already. You can still do it from scratch. It's not difficult. It's just a matter of let's do the 10 to 100%. Let's see where the peaks come off. I tossed this in here because I think people have gotten we've gotten too lazy in terms of columns. We call it a C18 is a C18 is a C18. That's not true. C18s are different from one another. There's some more subtle numbers that we can look at to compare columns. One of the numbers, and so this is a page out of the MacMod website talking about their different columns, and on it we are looking at things like the USP code. So USP, US Pharmacopoeia, they recommend columns for different separations, but they don't like to mention brand names, so they have generic names. L1. L1 is the C18 column, so C18, C18. But reality is, when you look at this, we're going to look at some other parameters. Particle size, obviously, you probably know what your particle size is. Pore size, we like small pores unless you're doing proteins. You got big molecules, we want bigger pores. We want 300 angstrom, not 100. So we can look at this chart and sort of tell more about each column. pH range, pH 2 to 9. My opinion, you stay pH 2 to 7, every column in the world is happy. You go above pH 7, yes, you go to run pH 7 on these columns. But read the fine print. There's certain mobile phases you cannot use, certain temperatures you can't use. So I'm not a big fan of going above pH 7 under any circumstances. Yes, you can, and the technology's out there to do it, but I prefer sort of staying in the below 7 range. Temperature max, we typically run columns at 40, max temperature out at 60. Above 60, we do more jams to the column. I highlighted one of the columns here. Carbon load, I think, is a really cool concept, easy concept that you could look at to evaluate columns. Carbon load is literally the percent carbon on the column. So if I were to take your stationary phase, weigh it, put it in a muffle furnace at 1,000 degrees, weigh it again, the difference would be the carbon that burnt off. So typically C18s are on the order of, I don't know, 17, 18% carbon. I've seen them range, the lowest C18 I've seen is a 7% carbon. The highest is a 30% carbon. C18s can range. If you're working with a non-base deactivated or non-NCAP C18, it's probably going to be more like 10 or 12%. If you have an NCAP C18, so look at these guys. These guys are all NCAP. NCAP columns tend to have higher carbon load because we got more carbon on the column. The more carbon you have, the more retention you get. The more it holds on to molecules. So if you want longer retention, we like higher carbon load. If you have a great big giant molecule, you have a C45 hydrocarbon, and you're saying, this thing takes forever to come off my high carbon load column, I'd say, well, let's get a lower carbon load. It won't stick as long. Usually we like more sticking, more interaction. That's why we usually like high carbon load. So that's a neat thing to look at. The other neat thing, surface area. These modern materials that we're looking at, 350 square meters per gram. That is 3,500 square feet inside column. So if you look at a regular column, it's got about a gram of material. We're talking about 3,500 square feet inside that column, like the size of a big house. Why is that so important? Where do we do the separation in chromatography? At the surface. More separation. Okay, so this helps us sort of figure out the right chemistry. And then when we talk efficiency, efficiency is all mechanical. Nuts and bolts, size of the particles, and the length of the column. So let's talk about that. And this is where we get into the sort of the LC theory part of the talk. I know what you're saying. Yay, LC theory. Okay, no one's ever said that before. I know no one's looking forward to the theory part. But at this point, you've stuck around this long, you're probably wondering, why do we like small particles? Why is there an optimum flow rate? Well, I'm glad you asked, because I'm about to tell you. What you've asked for is what's called the Van Deemter talk. This is the classical LC theory talk. Let me take you through this nice light look at theory. And what I want to show you is that we understand what's going in the column and we can be in charge of it. So the Van Deemter equation goes back to 1952. J.J. Van Deemter, working with a packed column GC, and he invents all the equations that we use to this day. So he's working with old homemade GC, and he's asking the question, why do peaks get broad? So let me take a next step. And he's looking at this just from an engineer perspective. He's saying, I make an injection in about a half a second, right? If you make a 1 microliter, it expands to 1 milliliter. I'm running 100 mils a minute through the liner. I can make an injection in about a half a second. But when the peak comes off the other end, it's like 30 seconds wide. Why does the peak get so broad? If we could understand that, maybe we could push back and minimize the broadening. So Van Deemter's whole thing was, how do I minimize this broadening that's happening? You could say he was a pessimist. He said the whole world, peaks are just getting fat all over the place. How do I minimize this? So he says, there's 3 things that make this happen. He calls them the A term, the B term, the C term. He says they're not related to one another. You need to minimize each one if you want to minimize this broadening. So he saw this as, we need to minimize this effect. So the A term, he called this eddy diffusion. Probably better to call it the multi-pack effect. And what he said was, you got a bad pack with particles. Now, this is 1952. This is the early day of GC, and they're working with packed columns. Now, as you'll see from these slides, you'll figure out why they went to capillaries. But in the LC world, we're stuck with packed columns. We're going to have packed columns from the down to the end of time. And because of that, this is still a major issue for us. So we have a column packed with particles. We make an injection, and every molecule has to travel through that packed bed. Now, molecules can't just zip right through a particle. They've got to go around them. So they've got to go left and right. So if a molecule hits a particle, it's a random choice if it goes left or right. So if you look at these three molecules here, molecule number one is just having an unlucky day. It's just bumping into things. So it bumps into that first particle and it goes down. Then it bumps in again, it goes up and then down and up and down and up, and eventually makes it to the other side of the column, but it's made a lot of left and right turns, traveled a little further than all of its friends, which means it comes off a little later than the middle of the peak. So it comes off towards the end of the peak. By the same token, I can have a molecule number three that's really lucky. It just happens to bump into almost nothing, chooses a very straight path, chooses fewer turns, which means it comes off a little earlier than all the friends. So remember, a peak is not 3 molecules, but 3 billion molecules. Of those 3 billion, most of them are making an average number of left and right turns. That's why they come off in the middle. That's why the middle of the peak is so tall. But some molecules take extra turns, they come off the end. Some fewer turns, they come off the beginning. And that's the first reason why we get a Gaussian distribution. We start with a square wave, but we end up with a Gaussian curve. So if we ask the question, how do I minimize this? This is going to happen. This happens every single day we do LC, but how do I minimize this? So if we take a look at my parking lot example. So this is me late last night trying to find a picture of a parking lot packed with cars, and I'm not very successful. But let me show you where this is coming from. And that is, I think about going through this packed bed. I'll take a step back. Going through this packed bed is like me walking through a parking lot filled with cars. So I can't walk through a car, I got to walk around it. So if all the cars are really teeny tiny, they're all smart cars, little tiny, those half-size cars, and I bump into a smart car, I'm not that worried because I can take a half a step and I'm already to the side. So I make very small changes in my path as I go through these smart cars, and I don't really change how the distance. Let's say I've made 100 turns and my friend makes 99 turns, but each turn is like a couple inches. It doesn't affect our final path. If, however, we're walking through a parking lot that's filled with a bunch of Winnebagos, a bunch of RVs, they're gigantic, and I bump into a Winnebago, I got to go all the way around it and then another one around it. So you could see that the deviation path, instead of making a little bit of a deviation, if I have to deviate a lot, if I make 10 turns, my friend makes 9 turns, another friend makes 11 turns, we take very different amounts of time to walk through that parking lot. So if we think about the parking lot packed full of cars, trying to walk around them, what we want is those cars to be really small. That's the particle size. So the A term, A is 2 times lambda to d sub p. Our goal is to minimize A. So lambda is packing factor, d sub p is the particle size. So I got a real simple mathematical question for you. If I want to minimize A, what size particle do I want to use? A big particle or a small particle? A small particle. That's a no-brainer. So I will offend half the audience here by saying I don't believe in the term UPLC. I think UPLC is a marketing term only. I think it has no scientific definition. I know. Have I pissed half you off yet? Okay, I'm going to keep going. I don't believe in UPLC because what is UPLC? UPLC is someone said, oh, if we make a particle smaller, it'll be better chromatography. Well, that someone was J.J. Van Deemter, and the year was 1952. So we think of this as something that was invented 10 years ago because the term UPLC came 10 years ago, but I would argue UPLC is HPLC. I mean, when I first started LC in 1980, we were using 10 micron particles. And then mid 80s, we went to 5 micron. And then we went 3.5 and 3 micron. And then we went 1.8 micron, but somehow that is a totally different technique. It's not a different technique, it's the same thing. So I believe that UPLC was invented in 1952. We just didn't call it that. But Van Deemter said from the beginning of time, you want skinnier peaks, you want smaller A terms, make those particles smaller. So 5 micron, still common, old-fashioned, but they're still common out there. 3 and 3.5, getting a lot of good use. The 1.8, so the UPLCs or UHPLC or whatever term you want to use, those are our new smallest particles. So you want to put on your prediction hat 10 years from now. What particle size are we going to use? Is it going to be greater than or less than 1.8? Less than 1.8. Oh my gosh, you can see the future. Yeah, we could all see that in the future, right? We're going to be using 1 micron particles. They've been used. Jim Jorgensen, professor, University of North Carolina, he's the guy who invented UPLC. I don't know if I can say that out loud. He's the guy who invented UPLC. Look at all his papers. He was the first one doing the ultra high pressure work. He's done work up to 80,000 psi. No one's in that range. So he's done the work up there. So it's not that it's not going to happen. It'll happen someday. It's difficult to do that. Okay, so we like small particles. That's the A term. The B term says I got what's called longitudinal diffusion or molecular diffusion. It means I have a billion molecules in the liquid state. They're dissolved, they're all together, and I want them to stay together, but they don't want to stay together because law of diffusion says they must move high concentration to low concentration. Molecules have to move from the middle of the peak to the ends of the peak. So we're fighting the law of diffusion whenever we do chromatography. Now in GC, this is the killer term. B term is a reason that limits GC efficiency. For LC, B term is not that big of a deal. It's there, it's important, but it's not as important because diffusion through liquids is so slow compared to gases. So the B term, 2 times gamma. Gamma is the tortuosity factor. B is the Einstein diffusion coefficient, and mu is the linear velocity of the flow rate. So if you look at that equation, we really don't have any influence on those other terms, but I can adjust the flow rate. So the B term is real simple. It says use high flow rates. Crank up the flow rate. If your peak spends 2 hours on the column, it's going to be fat. If it comes off in 2 minutes, it's going to be skinny. So use a super high flow rate. Now, before you run home and crank up your flow rate, you got to listen to the C term. The C term says, hey, C term is all about mass transfer. I've got a molecule, and I got to move from wherever I am to the particle, to the stationary phase. And once I'm at the particle, I got to diffuse in and out of it. So there's 2 parts of the C term, C sub S and C sub M for the mass transfer in the stationary phase, mass transfer in the mobile phase. It's sometimes called the C term, the D term. So wherever you come from, it's C and D or C sub S, C sub M. So the part of the stationary phase is really important. So think about this. I have a 10 micron particle. So the molecule, when it goes into this particle, it can go in as far as it wants before it turns around. Where it turns around is random. My whole philosophy in HPLC, GC, SFC is make all the molecules do the same thing. I want every molecule to follow the same path, do the same thing, but the molecules will not listen to me. I can't tell them what to do, but I can limit their choices. Let me give you an example. If I give them a 10 micron particle, 2 benzene molecules enter. This benzene can diffuse in 1 micron and come out, or 2, or 3, or 4, or 5, or 6. You get the idea. Lots and lots of choices, and they're going to take all those choices. If I use a 5 micron, fewer choices. I can't go 6 microns in, I'm already on the side. If I use a 1.8 micron, I can't even go 2 microns in before I'm on the other side. So the smaller the particle, the fewer the choices, which means the molecules do more of the same thing. It keeps them as a nice tight peak. So that is why, another reason why we're going to like small particles, because big particles give molecules too much room to wander around. We want to keep them all together. If we look at the mass transfer term, particle size squared, see D sub P squared, anytime you see a squared term, it means it's really, really important. So why is it a squared term? Well, if a molecule diffuses 4 micron in, it's got to diffuse 4 microns back out. So that's why this is exponentially bad, which means it's exponentially important to use small particles. So this is the whole Van Dienberg equation. You put the whole thing together. By the way, I just tossed this in here because I think it's a cool slide. This is the GC that Van Dienberg used when he did all those equations. See all those great big giant equations, the equations that predicted UPLC that we use today? Yeah, this was his GC. Hydrogen coming in, he's got a mercury manometer here to measure the pressure happening on. And so the column, by the way, is E, is the column, and it's sitting in an oil bath. That was the original chromatograph. It's a Wheatstone bridge at the end to do the detection. And based on that, he was able to derive all those equations. That to me is pretty cool because I'd have a heck of a time deriving those equations with a beautiful chromatogram, let alone big broad peaks and rubber corks and corks and that kind of stuff. So that was the original GC that he used. So the end of the Van Dienberg talk is the Van Dienberg plot. And I'll tell you something. I think everyone misses the conclusion of the Van Dienberg. First of all, most people don't stay awake long enough to get to the conclusion. But everyone misses out. Everyone says, oh, yeah, Van Dienberg, that crazy old guy, he said there's some optimum flow rate in LC. You got to operate the optimum. That's not what he said. He said there is an optimum flow rate in LC. It's the low point on that curve. The lowest point is the highest efficiency. Now, what we're plotting on the x-axis is mu bar is what he called linear velocity, what we call the flow rate. So in LC, that's the flow rate. So this says there's one flow rate that gives you the best efficiency. Operate too high of a flow rate, lose efficiency. Too low of a flow rate, lose efficiency. So that is really cool to know that there's one place that gives us the best work. Now, more importantly, let me show you the shapes of the Van Diemters. These are actual data plots. It's a 10 micron, 5 micron, 3 micron. Look at the shape of the Van Diemer. Look at how steep that slope is, how it goes from 10 to 5 to 3. Why is it so exciting to me as a chromatographer to see that flat Van Diemer? What that means is I could crank up the flow rate and not give away as much efficiency, as much resolution, which means I could do the same separation in a lot less time. If I double the flow rate, I cut the analysis time in half. Now, if you're running a 10 micron, you double the flow rate, you lose a lot of efficiency. 3 micron, you barely lose anything. So let me show you one of my favorite Van Diemer plots. These are actual data points. Every little square there is a data point. This is 5 micron, 3.5, and 1.8. When you look at the 1.8, you realize, oh my gosh, it's nearly flat. 1.8 at its is at 5 mils a minute is better than 3.5 at its optimum. So that means you could run anything. If you switch from a 3.5 to 1.8, you crank up the flow rate 5-fold, you'll get the right results in 1/5 the time. Now, I'm not saying you physically do that on your instrument, but that's why this is so interesting. So UPLC, everyone missed the boat on UPLC. Everyone, if you ask anyone out there, what is UPLC for? You'll catch people by surprise. Be able to say, well, UPLC is it's fancier. It's you know what it is? It's higher efficiency. I learned that as higher efficiency. That's not very exciting. I can give you high efficiency. I can string columns together and give you any efficiency you want. That's not very exciting. What's exciting is high efficiency per unit time. This is what UPLC means. UPLC is the fact that that's a flat Van Diemer. So if you bought a UPLC column and you're running 1 mil a minute, boy, did you waste a lot of money because you're not taking advantage of it. If you're doing UPLC, you want to be up there on that Van Diemer. You want to be 2, 2.5. You want to be as high as you can in the flow rate because no flow rate is ever going to affect your resolution. Is only going to make your analysis faster. So to me, UPLC is high efficiency per unit time. So we want short columns, high flow rates, ultra fast analysis. That's UPLC. UPLC is not getting 50,000 plates. I used to work for Amoco 35, 40 years ago, big oil company, and I strung 3 30-centimeter columns together because I was a boy and decided 1 is good, 2 is better, 3 is better. So I three together, had to heat it up to 90 degrees to get flow going through it. It took like 6 hours to run through it, but it was like 50,000 theoretical plates, the most ever generated. It wasn't practical, but it was a lot of plates. So what's important about UPLC is efficiency per unit time. Flat Van Diemer. Okay, so this is a slide that I took from my, I've been teaching this forever, 1990. This is my ACS course, 1990. That's baseline separation in 5 seconds, actually 8 seconds for the last peak, done in 1990. So when I show you this chromatogram, it's not like someday you too will be able to do work in less than 10 seconds. Well, that day was a long time ago. So if we have the technology to do this, this is out there. People just don't seem to want to take advantage of it. I think people don't know what's out there. So here's the deal. This is what UPLC is all about. We want smaller particles, shorter columns, higher flow rates. That's the key. That's the sequence. Okay, so I'll show you some pictures of silica. Irregular silica. That was 1970. That's what it was. They dug it out of the ground in some open pit in California. They're called diatoms. They're little animals that lived millions of years ago, and their skeletons are made out of silicon dioxide. So they dig them up out of the ground, they grind them, and they sieve them, and the good particles are used to make toothpaste. So when you brush your teeth in the morning, it's a million-year-old animal that died, so you can have clean teeth. That's pretty gross, right? So the things that were not good enough for toothpaste, the fines that fell through the cracks, were used to make HPLC columns. True story. LC column industry started with the rejects from the toothpaste industry because why? Silicon dioxide, it's sand, it's a rock, it'll withstand high pressures, it's high surface area. It's got all these great characteristics. Not all great, but a lot of great characteristics. So irregular, 1970s, fantastic. 1980 comes around. DuPont says, hey, we can make silica. We're a chemical company. We can make it and make it spherical. Once this came out, it was a no-brainer. There's no reason to use irregular if you could have spherical available to you. So now I got to tell you some really weird thing about the column industry, and that is the number 1 rule is to never change your column. Never make it better. Now, it's not the column company saying that. It's you, the customers, who are requiring that. So you don't want the column. You buy a new column this week and the same columns you bought last week. You don't want it to be a different column. You don't want it to be different. You don't want it to be better or worse. You want it to be the same. So if you're making columns with like Waters makes the microbonded pack, it's made out of irregular particles. They still sell it today. It's still irregular particles. They can't change it to spherical. Even though spherical would be better, it would change it and would invalidate all the methods that are out there. So that's why we have so many columns out there. Most columns, oh my gosh, how can I say this out loud? Half the columns out there are old-fashioned, lousy columns. You shouldn't be buying them. The other half are great columns, and all the columns are the same price. So you should buy the great columns and not the lousy columns. So irregular is out. Don't want to use those. Next one, spherical, 1980s, no brainer. 1995 comes along and we come up with called high purity silica. High purity silica is silica without heavy metal impurities. It's a no-brainer. There's no reason to use low purity if you have high purity. So columns invented before 1995. Can they use high purity silica? Nope. They use dirty silica. We don't call it dirty. We call it type A. Type A silica is dirty, old-fashioned stuff. Type B, they call high purity. Type A, they never called low purity. So we're seeing that there are columns out there, and we can choose the right ones. We got to sift through the bad ones, and there's some really good ones out there. This is really cool. This talks about monodispersed versus polydispersed. My job, our goal here is to pack a column full of particles, and we want to leave no empty space. So this is my, I don't know how this is going to come out of camera, guys, but this is my attempt of explaining this. If I have a bunch of gigantic particles, they don't pack very well. See all that empty space? Every time you see empty space, that interstitial volume, that's going to allow peaks to broaden out. So that's bad. So if I use smaller particles, ooh, there's still empty space between them, but a lot less empty space, they pack more efficiently. I go to smaller particles, and you're like, wow, I don't know, can you see that? Wow, there's even less empty space. And I don't know, can I jump to this one? And look at that, there's like almost no empty space. So you get the idea that the smaller the particle is, the more spherical it is, the more uniform size is, the more efficiently it packs. So this is some of the MacMod material is the monodispersed material, and they're very proud of this because of the fact that it's monodispersed. If you take an electron micrograph of polydispersed material, you could see there's different sizes in there, right? You can see some little ones hanging out in there. The little ones are the worst ones because they float to the bottom of the column and they tend to plug up the frit and they tend to cause higher pressure. So we don't like polydispersity and because it doesn't pack as well. If we look at just this is a Coulter Connor, this is actually looking at particle size. We're looking at this and we're seeing that the monodispersed gives us a very, very narrow range of particle sizes, whereas the polydispersed ones broader range, which is going to give us broader peaks. This is data, Van Deeper plots, if you want to see the sort of actual data. The monodispersed one on the right, you see the curve is lower than the polydispersed. So the lower it is, it's significantly lower, right? It gets all the way down to 6, and this guy is sort of hovering more around 8. That's because of the monodispersed particles. This is the manufacturing process. Thank you guys for giving me that. I got this from the MacMod guys. Like, most people don't share this technology, but I don't know if you did it by accident, but this is cool. This is sort of, how do you make little particles? This is one of the cool ways they do it. This is, you're packing a column with small particles, monodispersed versus polydispersed. What happens is peaks broaden out in the polydispersed. So that gets us to this concept of the smaller particle, the better. But what is the limitation? Why don't we all go to 2 micron or sub 2 micron? Because I could show you a 15-minute run on a 5 micron particle versus a 1.5-minute run on a 1.8 micron particle. So this is impressive, but it requires pressure. So the thing I've circled there, beautiful separation. This is less than a minute, gorgeous separation, but that requires over 15,000 psi, right? 100,000 bars, 15,000 psi. More than 15,000 psi, which means probably not going to do that on most instruments that are out there. So is there another way? There is something called superficially porous particles. They have trade names like connectics or a porous shell. And what they are is every particle we've talked about so far is totally porous. We call them TPP, totally porous particles, or TPS, totally porous silica. And that means this is completely porous, just like my Nerf balls. But the porous shell particles means that I have a hard shell, I have a hard core, like a marble, like a glass marble, and then I have sort of a crust on the outside, and the crust is the diffusion path. So if you think about it, this particle is the solid core is 1.7 micron, the crust is half a micron on each side. So the molecule sees a half a micron diffusion path, right? That's what I can see. But the pump sees a 2.7 micron particle. So we get the pressure of a 2.7, and we get the efficiency of a much smaller particle. So this is, in a way, sounds like a panacea. We really do get higher efficiencies than a normal particle. Is almost the same as a 1.8 micron. We really do get lower pressure, so you could run this on a regular instrument. The downside, though, is the capacity. Capacity is how many molecules can the column hold. If you think about it, if this thing is totally porous, I got a lot of stationary phase. If this thing is only just a crust of stationary phase, it's not as much, and it gets overloaded. So if you're injecting dilute samples, everything's great. But if you look at the column, the evospheres, the MACMOD columns, this is the totally porous. What happens is, as you increase the amount you inject, we still get the same efficiency. In this case, as we go from, it's 1,000, 2,000, 3,000 ppm, we lose efficiency during each one of those. So that, to me, is the challenge of the superficially porous particles, is that they don't have nearly the capacity of a regular particle. So they're great. I'm not against that. I guess I'm a silly statement. They're fantastic. It's a great way to get a high efficiency if you have an older instrument. Just be careful not to overload them, or you'll notice they overload a lot more easily. Okay, theoretical plates. It's all about making that peak skinnier. We could do separations on that on the porous shell particles, on those superficially porous particles, but usually we're always going to have better capacity on the normal ones. So, sort of conclusion of this, you can take a method. This is a real project that these guys are about to do tomorrow, and that is, I can give them a sample, and it's typically that run up there. It's a 15-minute run, and they're going to do it. They're going to see how fast they can do it. And I hate to show them this because this is a 30-second chromatogram. So, okay, that's a goal, guys. I guess you got to figure out how to do the sample less than 30 seconds. So, no, you don't have to do it less than 30 seconds. So, I want to say thank you to you guys, the MACMOD guys. Jeff and Ed at MACMOD, the chromatography bros. They're a lot of fun to hang out with. If you when you see them, they're at MACMOD all the time. When you hang out with them, just put them up against each other. See if you ask, hey, which one of you is taller? Which one of you is better at basketball? Which one of you can hold your breath longer? They're really competitive, so that's hilarious. You just, which one of you can flip this coin more times? And they'll be sitting there, they'll be competitive with it. So thanks, you guys. Thanks to the folks at MACMOD. If anyone out there has questions, send me questions. If you want to take a hands-on class from us, you can visit us here in Chicago. We teach the hands-on class, maybe 10 times a year. It is comprehensive. You get to run the LCs and the GCs and take them apart and put them together and learn a bunch of stuff and maybe have some fun along the way. So thank you guys for sitting around and spending your lunch hour, spending your afternoon with me. I'm happy to answer questions. So at this point, Alex, I'll toss it back to you, and you can take it from there.
Thank you, Dr. Polite. That was an excellent presentation. I have to say I am jealous. I will not be spending the rest of the day in class with you. So people in class are very lucky. As Lee was saying, we'll now move into the question and answer portion of the presentation. Please remember you can submit questions through the Q&A window, and we will take as many as time allows. Also, we will send out a recording of this presentation and the slides sometime next week. Okay. So I know you had mentioned, Lee, that you wanted your class to have a question. Is there one in there that we can start with?
Of course, there's going to be one here. Who's going to be the bold one to do that? I really do have a question for you. Go ahead.
The best way to control the charge of an analyte while it passes through the column?
Ooh, great question. What's the best way to control the charge of an analyte as it passes through the column? This is going to become really important for acids and bases. These acids and bases can exist in two forms. They can be ionized, they can be neutral. Ionized forms are very water soluble, don't hang out too much with C18s. Neutral forms hang out with C18s, not nearly as polar. So we want to control the ionization. Don't let the analytes control the ionization. We control it with a pH. So an easy way to think of it is, if you want your analytes to be neutral, call this ion suppression. I always remember acid is for acids. If your analyte is an acid, you're going to put acid in the mobile phase. The low pH will suppress your ionization. You'll be totally neutral, and you're going to look great by reverse phase. So acid for acids. Bases are a little more challenging. And you know what? I'll give you an answer, and then I'm gonna just leave you hanging there. But I run all my bases at low pH as well. I know it sounds backwards. Yeah, I got to show you an ionization curve to prove it to you. But all acids, high pH. I'm sorry, all acids under acid conditions, low pH. All bases I run at pH 2 at low pH as well. They are ionized. They are ionized. I'll give you that. But if you choose the right column, a good end cap column, ionized bases will often give you a bad peak shape. But if you have the right column, they do not give you a bad peak shape. So my approach now is everything at pH 2. That's my starting, and then we'll adjust from there. Yeah, that's a good question. Yeah.
Okay.
So
So one question from the online audience. When you refer to end capped, what do you mean by that?
oh, very good. What is end capping? So how do I do this as a hand wave? Let me see how I can let me see how I can do this. I have a slide show you. So you think about the surface of this raw silica, this silica gel or the spherical silica. Think about the surface. It's SiO, SiO, SiO. It's a polymer. It's a natural polymer, a siloxane polymer. Hanging off each silicon atom is a hydroxyl group, is an OH. So this is called silica gel. You find a packet of this stuff in your pocket when you buy a new jacket or your aspirin tablets. It's silica gel. It says do not eat. Yeah, eat that, by the way. Who would pick up a? I don't know what this is. Let me. Infants. We're gonna put it in our mouth. So silica gel it's got a bunch of hydroxyls, OHs on it, and it attracts water. So that is raw silica. It turns out that's a terrible stationary phase for us because we want a non-polar stationary phase. We want a C18. So the manufacturers, the folks at MacMod, they put a bunch of C18s, they bond all the hydroxyls and make them C18s. Well, not quite all the hydroxyls. They leave some behind because of bonding density, because steric hindrance. So I've got some, we'll call them hotspots, bad guys right here. It's a silanol, SiOH. We don't like that SiOH because it's very polar and it's actually a weakly acidic. So the hydrogen could dissociate, the oxygen is negative. So I have a natural, our columns are naturally a negative surface. If you have a positive analyte like a base, it's going to stick, positive negatives, Coulombic attraction, it sticks. Adsorption is what I call like Velcro, easy to stick and hard to let go. So it causes a tailing peak. So if you have residual silanols on the column, it makes acids and bases look terrible. So column companies know this. This is big business. So the folks at MacMod do the next step and they say, let's come through with another chemistry, trimethylchlorosilate, tiny molecule, and it's going to go and it's going to cap off all that hotspot, all the hotspots, all the bad guys. So we call this end capping. These were capping off the end or the bad guy. There's other slightly different ways. Steric protection is another way to do it, but end capping is by far the most popular. So I'm a big fan. If I were to say my number one choice of column is a good end capped C18 or a good base deactivated. I like the term base deactivated, it's more generic, but a good end cap C18 is going to be your best column for acids, bases, neutrals, for almost everything. It's going to be your one-stop shop. So end capping means let's cover up those hotspots. Favorite question of the day. Thank you. Sorry. That was better. Yep. Sorry. I'm sorry. It was just a better question. I've offended people in the room. I made them mad. Okay. Other questions?
Yep. Next question. How do you select the best solution or solvent for cleaning your HPLC columns?
Yeah. How do we clean an HPLC column? So I always think of it as we need a strong solvent. What is strong? Strong is defined as something that's more similar to the stationary phase. If your stationary phase is nonpolar, the more nonpolar your solvent is, the stronger it is. So water is the weakest thing. Methanol and acetonitrile are much stronger. So here's my simple answer. This is for reverse phase columns, silica-based reverse phase columns, most of the columns out there. If you got your column dirty, we can wash it off. So I say, here's my step. Step one, I wash with a high percentage of water. It sounds backwards, but I do 90-10 water acetonitrile because water is a good solvent for buffers, salts, azo dyes. So anything super polar that is accumulated, we're going to get it out with the water and then step it up to 100% acetonitrile or 100% methanol, whichever one you're using. Let it sit at 100% for an hour. I like to do this at 60 degrees Celsius. So at 60 degrees Celsius, 100% acetonitrile for 1 hour, there are very few things on this planet that can stick to your column that long. So I feel that if you do that, you have essentially a brand new column at the end of it. If you have really dirty samples and you're like, gosh, my column always gets crowded up, we'll do a gradient. And after at the end of every gradient, step to 100%, wash the column and then go back. So do a 5-minute wash at the end of every run. That will keep your column clean forever. That's overkill for most of us. For the rest of us, I don't know, once a week, once a day, you want to clean the column, you do that procedure. The 90-10 water acetylnitrile or water methanol, 60 degrees, 1 ml a minute, and then do it again. Do it an hour with 100% acetylnitrile. Yep, that's a good one.
Okay.
Silica-based reverse-phase columns.
We'll take one more question here. There's a lot, but be respectful of Dr. Polite's time and everyone else's. So this person's analytes have very similar polarity and are not fully resolving. Will putting two of the same column in tandem help with resolution?
Yeah, boy, great question. So the question is, I got lousy resolution, and can I put two columns in series? Answer is yes. If you double the column length, you double the efficiency. If you double the efficiency, you don't double the resolution. It's a square root term, but it goes up by the square root of 2, 1.41. So every time you double column length, you will get 40% more resolution. Absolutely true. You will also get twice the analysis time. So the downside to double length is you double the analysis time, but no question that if you're in that situation where you need more resolution, absolutely use the second column. I always say, the smarter way to do it is use a smaller particle. I don't know if you can do that, I don't know if you're allowed to do that, but a smaller particle half particle size will also double your efficiency, and it will not take longer. So I would first look at, can you buy a smaller particle? And then, or either way, I have no problem at all putting two, like I said, I put 3 together once. Don't recommend it, takes too long, but yes, you could do that. Watch your pressure, because you're doubling the pressure requirement of the instrument. A cool little trick to decrease pressure is you could heat up the column a little higher. So 2 columns in series run at 60 degrees instead of 40, and that brings the pressure way back down. So yeah, I'm totally up for it. I hope it works. I think it's a cool idea. Send me a chromatograph. Send me a picture.
All right. Unfortunately, that is all the time we have for today. We did have a lot of questions that we did not get to, so we will certainly consult with Dr. Polite and we'll get an answer to you on those.
Yeah.
Dr. Polite
I guess you just have to invite me back again to give another talk. I guess that's the only way we're gonna.
Well, we've gotten a lot of thank yous for the great presentation, so I don't think we'll have an issue doing that again.
Excellent.
But Dr. Polite does have an upcoming course September 15th to the 19th. And in our follow-up email, we will have a link on how to register for that if you're interested. As I said before, I've attended the class and it's certainly not something you want to miss. MacMod will also be presenting a 3-part 20-minute webinar series on monodispersed particles at some point in September, given by our CEO, Jeff Faden. And we will have details about that also in the follow-up email. Dr. Polite, thank you so much for a practical and insightful session, and to all of you for joining us and for all of your thoughtful questions.
Awesome. Hey, you guys, give my best to Ed and Jeff, the chromatography bros.
Will do. All right, have a great day, everybody.
Sure. Awesome. I believe we're done. Yay.